At 1 p.m., Ship A is 160 kilometers west of Ship B. So I'm going to draw a picture, a number line, showing point A 160 kilometers west of B. That's in the diagram. Now, Ship A is sailing east at a rate of 35 kilometers per hour. So Ship A is going east along this number line, and Ship B is sailing north at a rate of 30 kilometers per hour. How fast is the distance between the ships changing at 3 p.m.? Note that 3 p.m. is 2 hours after 1 p.m. Now let's utilize our 4-step process for solving related rates problems. In all these parts of these pencasts in this series, we're utilizing this 4-step process. The first step is to write down each rate in the problem as a derivative. So, one rate is 160 kilometers. No, that's not a rate, is it? That's a common mistake. But it's not 160 kilometers per time. I want to look for the rates. So one rate is what? 35 kilometers per hour. And another rate is 30 kilometers per hour. And then the rate I want to find is the rate at which the distance between the ships is changing. We're going to do this problem as usual in general and ignore specifics such as 1 o'clock, 3 o'clock, 160 kilometers. Those are values that will be plugged in at the end Now, what's different about this problem from the problems we've been doing in the first 5 parts? We need to define some variables, don't we? In order to write these rates as derivatives, we need to define some variables. In other words, this 35 kilometers per hour is the derivative of something with respect to time. But what? And this 30 kilometers per hour is the derivative of something with respect to time. But what? And similarly for this third rate. So I need to define my variables. Well, what is changing at a rate of 35 kilometers per hour? Look back at the picture. A is moving to the right. Ship A is moving east. So point A is moving along this horizontal line segment to the right. So couldn't I let X be the distance to the right of where ship A originally was? So isn't X increasing over time? Ship A is moving to the right. This first dot here indicates the original position of ship A. This second dot here indicates the position of ship A at time t, where t is some positive value. So wouldn't this X be increasing at the rate of 35 kilometers per hour? Yes, so dx dt is 35 kilometers per hour. Now, you can use any variable you would like for this distance between A originally and later in time. But since this is a horizontal distance, it makes sense to use x, so I choose x. Now, what's changing at a rate of 30 kilometers per hour? Point B, ship B originally was here as indicated by this dot labeled B, but then ship B is moving north over time. So it makes sense to let y be the distance north of the original location of ship B at time t, where t is a positive number. Okay? Now, y is what? Increasing instead of decreasing, right? So, dy dt is a positive 30 kilometers per hour, just like dx dt was a positive 35 kilometers per hour, because x is getting larger and y is getting larger. Now, I want the rate at which the distance between the ships is changing. So I need what's changing here, the distance between the ships. So I need to label that distance. Now, I could use z, or I could use capital D. It's your choice. I'm going to use capital D. Now, this isn't the only choice of how we could have set up our variables. We could have let, notice we have a right triangle, don't we? And we could have let this side right here, the side right here, we could have let this side of the right triangle been x, if we wanted to. But then dx dt would have been what? A negative 35 kilometers per hour. It's totally up to you how you define your variables, but you need to write down how you're defining them and clearly label them in a picture. Now, that's step one. Step two is to look at the derivatives in step one and identify the dependent variables. Well, the dependent variables in the derivative notation in step one are x, y, and d. I need an equation that relates x, y, and d. Well, I see a right triangle here. That makes me think of Pythagorean Theorem. But I've got a problem. This x is not one side of this triangle, is it? D and y are sides of the triangle, but x is not. Oh, but wouldn't this side of the triangle be 160 minus x? Now, if you had let this side of the triangle be x to start with, then this little piece that's labeled x now would have been what? 160 minus x. Okay, so the equation that relates x, y, and d is 160 minus x squared plus y squared equal d squared. Pythagorean Theorem. Now, step 3 says to take derivatives of both sides of the equation from step 2. But take derivatives with respect to our independent variable t. The derivative of a sum is the sum of the derivatives. Now, remember here, x is a function of t, right? X is changing over time. Y is changing over time. They depend on t. Now, this is a composite function, 160 minus x squared. The derivative is the derivative of the outside times the derivative of the inside. Now, what am I taking the derivative with respect to? T. I'm showing every step one by one. Chain rule. The derivative of the outside is 2 times 160 minus x to the first power. Then I multiply by the derivative of the inside, the derivative with respect to t of 160 minus x. Okay, the derivative with respect to t of y squared. Well, the derivative of the outside is 2y, but the derivative of the inside is dy dt. Remember, y is a function of t. And similarly, for the derivative with respect to t of d squared, derivative of the outside is 2d. The derivative of the inside is derivative of d with respect to t. Now, what is the derivative with respect to t of 160 minus x? Well, the derivative of the outside is, well, the derivative of a difference is the difference of the derivatives. Let's view it this way. This is the derivative of a difference, so it's the difference of the derivatives. So the derivative of 160 with respect to t is 0. But I've got to take the derivative of x with respect to t. And these are all with respect to t. The independent variable here is always t, even though my t's, I realize, sometimes might look like z's. I'm not using a z in this problem. Okay? Now, notice I could divide both sides by 2, couldn't I? We don't have to do that, but that's going to make the arithmetic easier. And I'll just put this negative out front. Dividing both sides by 2. So, from step 3, notice I have an equation, negative quantity 160 minus x times dx dt plus y times dy dt equal d times derivative of d with respect to t. That equation relates the derivatives in the problem. It relates the rates in the problem. So now step 4 in this 4-step process for solving related rates problems is to substitute the values that are specific to this problem at the specific instant in time that I'm interested in and solve for the requested derivative. I want to solve for the derivative of d with respect to t. So I should either be given everything else. Now notice I'm given dx dt in step 1, dy dt in step 1, but I've got to find the x and the y and the d at the particular instant in time, 3 o'clock. Now, note this equation out of step 3 shows how the derivatives are related at any time. So, if the problem had said, how fast is the distance between the ships changing at 5 p.m. or at 1:30 p.m., this equation would apply. But step 4, I have to figure out the x, the y, the d at this particular time, 3 p.m., that they're asking us about. So, at 3 p.m., what is x? Well, look back at your diagram. X is increasing at what rate? Look at step 1. X is increasing at a rate of 35 kilometers per hour. At 3 p.m., how long has the ship been traveling from its original position? 2 hours, right? 1 p.m. to 3 p.m., 2 hours. If ship A travels for 2 hours at the rate of 35 kilometers per hour, X is going to be 35 kilometers per hour times 2 hours. So that's going to be 70 kilometers. So at 3 p.m., X is 70 kilometers. At 3 p.m., Y is, well, Y, look back at step 1. It's increasing at the rate of 30 kilometers per hour. And at 3 p.m., that's 2 hours that the ship has traveled after being at its original position. So it has traveled 60 kilometers in those 2 hours. Now to find D, let's look back at our original picture. I can use Pythagorean Theorem. I've just copied my right triangle from my picture at the beginning of the problem. So at 3 p.m., this is the right triangle freeze-framed in time at 3 p.m. Y is 60, and that's kilometers. Now, what's this side of the triangle? What's the horizontal side of my triangle right here? Well, at 3 p.m., X is 70. So this has to be what, 90? Notice this side of the triangle. This side of the triangle is 160 minus X. So if X is 70, then 160 minus X is 90 kilometers. And I want to find D. So by Pythagorean Theorem, D squared equals 60 squared plus 90 squared. So D is the square root of 60 squared plus 90 squared. So that's going to be the square root of 11,700 kilometers squared. So that's going to be kilometers. And let's not use decimals yet because I don't want round off error to propagate. But I could write this as the square root of 117 times the square root of 100. So that's 10 times square root of 117 kilometers. That's what D is at 3 p.m. Okay? So now I'm going to take my original equation from step 3. I'm going to rewrite my equation from step 3. And I'm going to plug the values into there for 3 p.m. So X at 3 p.m. is 70. Dx dt is 35. Y is 60. Dy dt is 30. Notice that's from step 1. My d is 10 times the square root of 117, and I want to solve for the derivative of d with respect to t. Now, I was running out of room here, or I would have written my units. We do need to pay attention to units. What would the units be here for the negative 160 minus 70 times 35? Well, the negative 60 minus 70 would have been kilometers, and the 35 is kilometers per hour. So when I multiply, I would get square kilometers, kilometers squared per hour. Same thing for the 60 times 30. It's 60 kilometers times 30 kilometers per hour. So the units there would be kilometers squared per hour. The units for 10 times square root of 117 is kilometers. So I want to solve the equation for the derivative of d with respect to t, because that's the rate in step 1 that we want to know. So that's negative 90 times 35. So that is negative 3,150 kilometers squared per hour, plus 60 times 30, or 1,800 kilometers squared per hour. But I need to divide both sides by 10 times square root of 117 kilometers. When you compute that, you get negative 1,350 over 10 times square root of 117 kilometers squared per hour divided by kilometers would be kilometers per hour. Well, I can divide numerator and denominator by 10 to get a negative 135 over square root of 117 kilometers per hour. And that's approximately negative 12.48 kilometers per hour. Now, what does it mean that our derivative of d with respect to time was negative? The rate at which the distance between the ships is changing is a negative 12 48/100 kilometers per hour. So that means at 3 o'clock the ships are getting closer together at that rate.